the second time slot, and then the corresponding 3 parity bits, and in this case again it's 0, 0.
Oh, hey Holden.
Hey, what's up, Rayaan? You ready to work on this project?
Oh, I'm so ready to work on this CSE project.
I've been having such really good ideas. I think we should take a shot at Niagara Falls. One thing I really want to do for this project.
Oh, Holden?
So we should have it in the background. We can have some over voice dubbings.
Where'd you go, man?
We have this really cool diagram we're going to put on the board. It's going to be sweet. Oh, hello?
Wireless communication is everywhere around us, from phone calls to FaceTimes. But how can we be sure the video we live stream from our computer arrives the same at its destination? Any data we send wirelessly is bound to face interference and noise, making it prone to errors en route. Most traditional error correction methods break the text you send into small, even slices, like a loaf of bread, and checks each slice for any issues. But this is too slow to work for things like phone calls or live streams, where data is continuously flowing like a waterfall.
So what's the solutions? Convolutional codes. Now, before we jump in, if you aren't familiar with Boolean logic, how to compute Hamming distances, or the basics of finite state machines, it may be helpful to check out the videos here, here, and here. Convolutional codes work by adding redundancy to the waterfall of information being sent, using something called a sliding window.
We slide this window of a size k over our input bits, which is our sent message. Each window generates R parity bits, combining current and previous bits with XORs. The bigger the window, the more parity bits we get, and the greater our error detection. But we have to be careful. As we increase the window, the message size also increases by a factor of R, and the decoding takes longer. So it's important to pick the best happy medium between maximum error detection and reduced message size. Over here we can see the encoder in action. So we're going to start with our first bit. This is our sent message, and our first bit is going to be slid into the window, and then there are going to be 2 empty spots in the window, and those are just going to be like zeros. So the window is going to come over here, and we're going to generate our parity bits. So our first parity bit is going to be 0, 0, 1, and it's going to generate a 1 parity bit, which is here. And then over here, it's going to generate another 1 parity bit from these two, 0, 1. Then the window is going to slide over. Slide this way. So the 1 here goes to the middle now, and the 0 is going to come down. And then it's going to go through again. 0, 1, 0, generate a parity bit of 1, and a parity bit of 1. This is going to continue on for the entire message.
After our message is properly redundant and sent off flying through the sky until it's caught by a receiver at its destination, the outdated way to decode this message is by comparing it one by one on a table of all possible encodings and picking one with the closest Hamming distance as correct. As you can imagine, this is insane, especially as we get larger messages in a bigger window. Possibilities are endless. So here we have an example where we have a message of window size 4, and every time you add another bit to the end of the window, obviously the table is going to double in size. So if we had a window of 8, we would have 2 to the 8 possibilities to compare to, and this is only going to keep growing. So here we have our encoded message, which has absolutely no errors, and here is the message we have actually received. As you can see, it doesn't match anything one-to-one in our table, but we find the Hamming distance is the lowest when the message 1011 is sent. So in this situation, we would take 1011 as our decoded message. This is not feasible. So if that message is too slow to properly stream our data, what now? Well, instead of wasting our time and energy, we can use a trellis diagram using the Viterbi algorithm to properly decode our message. A trellis diagram is a finite state machine that keeps track of our most likely decoded message at every window. We keep track of the most likely character from each sent window by comparing the Hamming distance between the received message and what the message is required to reach the next state in the diagram. Here we are going to walk through our sent example with no errors. So the way it starts out is we start at this state up here, and it's impossible to reach these states down here.
Before we get into the next section of our video, let me explain what some of these numbers mean. So over here is going to be our sent message. This is what we're trying to decode. So over here we've got 2 bits, 0 and 1. Now these are 2 possible options to try to figure out the sent message. So if we were to guess that it's a 0, it would go this way. Based on the previous bits, which right now is like 0, 0, 0, we would generate a parity bit of 0, 0, match that up with the sent message, and we see a difference of 2, which is going to give us a Hamming distance of 2. And over here, if we guess that the first bit is going to be a 1, that's going to generate the parity bits 1, 1, and the Hamming distance is going to be 0.
So in the diagram, we start at this top state, and every time we have a message that is sent with a 1 bit, it goes down. Every time there's a message with a 0 bit, it goes up. Now, as you can recall, our first bit that we sent was a 1, which produces the parity bits 1, 1. So we're going to send 1 and we're going to go down, and the resulting parity bits is 1, 1. And that distance between 1, 1 and the ones that we get from sending the 1 is 0. However, let's say we are considering that it might be a 0 that we sent initially. Well, we see that sending a 0 produces parity bits 0, 0, which has a distance of 2. That is less likely, but we want to keep track of it anyway, so we're going to send the 2 further down the line. Now here, we have two possibilities in this state and two possibilities in this state. We could either send a 1, which would produce the parity bit 0, 0. That doesn't happen because we are trying to compare it with our received bits 1, 1. So we keep track of the distance 2, add it to the previous distance, and that state has a Hamming distance of 2. Or we send a 0, which produces the parity bits 1, 1 from our sliding window, which goes up, and the distance remains 0. We want to keep track of this minimum distance, even though this state does connect up here, because going from this state to the next state is going to produce Hamming distance of 2, which would be added to 4. But if we had a 4 here, we can't backtrack to find properly what our message is. So as we can see, we start in our first state, which we can either send a 0 or a 1. If we send a 1, we get the parity bits 1, 1, which matches what our encoded message is. So we're going to keep track of the Hamming distance in the next state and say it is 0. Now let's say we believe that we're going to send a 0. Well, it can't be 0, because if we sent a 0, we would have a Hamming distance of 2, which does not match our transmitted message at all. So we keep track of the 2, and we keep going down the line. So let's say our next bit we want to find is if it's a 1 or a 0. Windows slides over, and we now have a message 1, 0, which produces the parity bits 1, 1, which matches exactly with what our transmitted message is. So we can go up, keep track of the 0, and we also have the possibility of going down and seeing if another 1 is sent. Well, that would send the parity bits 0, 0, which is Hamming distance 2 away from our transmitted message. So we keep track of this, add the Hamming distance of 2, and put it in the next state. And so we keep track of this all the way down until we reach the end of our window. This will be ever growing as more messages are being sent, but you track it the whole way following the minimum distance. And as you can see, with no errors following our decoding, we have 1, 0, 0, 0, 1, 1, 0, which is the same as what our encoded message is over here. And so wait a minute, what's that? That looks like an error. Well, that's something our diagram is able to resolve, usually. In this scenario, we don't have a strong enough sliding window or rate to properly decode the message because it splits off into 2 equal Hamming distances. Our code kind of ends here. However, it does have the capability to detect there is an error in general, since our final Hamming distance of the minimum state is not 0. So somewhere around here, we can figure out where the error occurred, and here we find it's the 5th transmitted bit where we have our error.
Thanks for tuning in to our project about convolutional codes.
Make sure you check the description below for our resources that we used, as well as some videos that might be helpful in rewatching this video.